Okay, so present this paper called Flash Storage Disaggregation, and from these people at Stanford, Imperial College London, and Facebook. This paper was a while ago, EuroSys 2016. So a few of the things in it might be a little bit outdated. So at the time of this paper writing, Flash was just gaining popularity at the data center because of its lower latency and high throughput. So at the time, it was about 100,000 IOPS per sec, as they say in the paper, but now it's around 600,000. And as we know, Flash, it's being commonly used to support persistent KV stores at Facebook, LinkedIn, and now at many more places too. So it sounds good, but what was the problem? So what tends to happen is that the requirements of applications can change over time. So on the right, we have a graph here where we have in orange Flash capacity used by some KV stores at Facebook. And in the blue, we have the read throughput, and in the green, we have the CPU utilization. So if we look at the red circles, both the read throughput and the capacity of Flash are varying wildly over time for what are the same applications. So a problem we have is how do we effectively balance server CPU, memory, and storage to avoid over provisioning and wasting money. And how we might want to do that is through disaggregated storage. So instead of attaching the storage locally, what we can do is place it on another machine and then access the storage over the network. It's quite common now, but at the time it was more common for HDDs because the network overheads were small compared to an IO request on the hard disk. But as we know, Flash was enabling really, really low latency. So the question this paper wanted to ask, or one of them was, given these low latency Flash devices, can Flash disaggregation still be effective even with the network overheads? So if we have a low latency Flash drive, but a high network overhead, maybe the network overhead is actually more than the latency for the Flash, so maybe it's not so good. And just as an overview of what that could look like, on the right, we have local Flash, where we have what they call the application tier on the left, and then the data store tier on the right. So we have these application servers will send requests like get input for key values to these data store servers. And the data store server will host the key value store and have CPU and RAM, etc., but also have Flash attached locally. If we compare this to the right, where we have disaggregated Flash, like before, we have application servers and data store servers, but they don't have Flash attached locally. Instead, they communicate with Flash over the network, and this example, ICSI. So on the Flash server, we have some sort of remote block service and a Flash device itself, but we have much less powerful CPU and RAM compared to what's on the data store servers. So the applications might issue get inputs, and these data store servers issue read and writes to blocks. So three main questions they wanted to ask in this study were that, first, can a data center application or applications tolerate these overheads of remote access to Flash, given that Flash is so fast and low latency? With existing network storage protocols, it's not looking at creating a new protocol or something like that. And given a network storage protocol, how can we optimize this performance on a remote server? And given these optimizations, at what point does disaggregating Flash lead to either cost or resource utilization benefits? So just as the background for the application requirements in this study, it was done at Facebook, and RocksDB is used as the sort of primary store. And the workloads they test in this store, they say they're compute intensive. So they're serving complex queries and doing stuff like compactions, which uses a lot of CPU, as well as serialization and deserialization. And their applications have very high random read IO, and high write throughput, which Flash can, Flash can serve both. But I think maybe the most important point of the paper is that the tolerance they have for latency in these applications is around 5 to 10 milliseconds, not microseconds, which gives them a lot of leeway in terms of network overheads, as we'll see. So when we look for a remote storage protocol, we want it to look like a local flash device, and we want it to run on commodity or already available hardware. We don't want special hardware. We want it to scale to the data center, and we want it to be low overhead. So at the time, the options were network file system, some block I/O protocols like ISCSI, RDMA, and PCI-based fabrics. So they talk about each protocol in more detail in the paper, but just the most important or salient points they made were for NFS or SMB, and because all the storage was accessed through network file servers, they said limited the scalability for small key value accesses. ISCSI gives us the illusion of local block storage, but initially the non-negligible performance overheads. And what ISCSI does is just translates SCSI commands over the network. They talk about NVMe over fabrics in this paper, but at the time, they didn't choose it because it required specialized hardware. But from what I understand now, NVMe over fabrics is actually pretty popular. And they also mentioned PCIe fabrics where hosts can just communicate over PCIe over the network, but they didn't choose this because it's expensive. And so for this paper, they choose ISCSI. So even though it has non-negligible overhead, and it ticked all of the other boxes for the study and stuff like that. And there's a lot of them in the paper. So on the right, they modify a lot of, not modify, but tweak it in a way that they can gain really significant performance benefits. So we look at the graph on the right, we have 1, 3, and 6 tenants, which is just servers accessing remote storage, and they can almost triple the baseline performance just by tweaking the settings this time. So they use this throughout the rest of the paper. So this paper is a little different in that the evaluation is essentially half or more of the work. So we can just go into it right away. So they set up a cluster where it's 12 servers with 6 cores each, with 64 gigabytes of RAM, connected with 10 gigabyte network cards and connected with a 10 gigabyte switch. And in the study, their flash tier server, or the disaggregated flash server, is just a single server with a 400 gigabyte NVMe SSD. And how it works is that the application tier servers generate load to RocksDB on the data store servers, which goes to the flash servers, like the diagrams earlier. Little confusing the way the workload is described, but it's 2,000 to 10,000 read IOPS per terabyte and 100 write IOPS per terabyte, with 17 to 21 byte keys and 100 byte values just for the workload. But they change these parameters throughout the tests. Shit.
What is your Wi-Fi?
It's CSL at 516.
Oh, I think that is not that.
What are you on SNU? So first, we can look at the end-to-end performance when there's just one server accessing one remote flash server. And we have two graphs here on the right. Top one is just the client read latency with the default workload. And we have the latency on the bottom and just the CDF. So when we're accessing flash remotely, we see a P95 latency increase of about 260 microseconds, which is a lot, but as they say in this study, they can accept 5 to 10 milliseconds of latency with their target application. So it's still acceptable, even though compared to a modern flash disk, that's about 26 times the actual read latency. But it works for them in this study. But if we look at the bottom graph, they describe there's a 20% average drop in queries per second when we access the flash remotely. So if it's just one server accessing one flash device, maybe not so good. But if we move to multiple servers sharing one flash server, so it's just one disk partitioned, and multiple machines accessing the same disk, we still have these latency problems, and we still have a penalty. But when we double the amount of servers accessing the same flash server, we double the queries per second, but we're halving the cost of flash. So the performance is almost the same, but the cost of flash is halved compared to the case where it's just one server accessing one flash disk. So if we look at the graph on the top, it's the graph in the last slide where we have one server and the latency versus the queries per second. And so if we look at the graph on top, it's the queries per second and the CDF of the latency, the latency when it's just one server, and then at the bottom it's when we have multiple servers accessing one flash device. So we've almost doubled the queries per second, but it's the same flash disk, so we've halved the cost of flash. So if we just look at it in terms of numbers, we can say we can try to find out when does disaggregated flash become cost effective. So the example they give in the paper is they want 10 million queries per second, and we have 100 terabytes of data, and we assume 1.2 terabyte flash drives. So they make some assumptions about the costs in this paper. So we say flash on a server is $2,400, and CPU and RAM on a data store server are also $2,400. But the cost of CPU and RAM on a flash server, where we're just hosting the disks, are around $50 per tenant, and we assume 3 tenants. So for the local flash, if each server can do 50,000 queries per second, we need 200 servers with local flash. So it's 200 by the cost of flash and the cost of CPU and RAM. So it's $960,000. But if we make the same calculation with remote flash, it's different because the storage is provisioned differently. So on the flash server, we need 100 terabyte divided by 1.2 terabyte. So we need 83 flash servers compared to 200 servers with local flash, but we need 250 data store servers instead of 200 because we pay a penalty for the remote flash access. But each data store server doesn't have a flash disk; it only has CPU and RAM. So the calculation becomes 83 flash servers, which is 83 multiplied by the cost of a flash disk and the small amount of CPU and RAM for accessing the flash, and then 250 data store servers, but we just need to pay for the CPU and the RAM. So it's $812,500, which is 14% cheaper. So initially this took me a while to fully understand. So just try to explain it. What has happened in the case of the local flash is because each server can do 50,000 queries per second, that's what the CPU can do. So we need a minimum of 200 servers if we're using local flash. So what has happened is, because we're only using local flash, each server needs a flash disk, and we have over provisioned the flash compared to our storage needs, because we needed 200 servers for the compute needs. But in the bottom case, we were able to separate the storage requirements and the compute requirements, and thus we needed a lot less flash disks, and we saved a lot of money. So if we want to look at when it becomes really cost effective, not just a little bit cost effective, let's take the same example from before, where we need 10 million queries per second, 100 terabyte data size, and 1.2 terabyte flash drives. But we assume that flash is double the cost of the CPU and RAM, not the same cost as it was in the previous example. So when we're over provisioning the flash, we need 200 servers like before, but it becomes $1,440,000 for the local flash. But again, when we use the remote flash, we don't need to buy as many flash disks because we're not over provisioning as much, and we save about $300,000 in this case when the flash is more expensive. But what about when it becomes cost ineffective? So when is disaggregated flash not, or storage, when can it not be a good idea? So we look at the same example as before, but we have a 250 terabyte data size, not a 100 terabyte data size. And what happens is that, so we need 208 servers with local flash because it's 250 terabyte divided by 1.2 terabyte. That's the storage requirement we have, which is almost $1 million for the local flash. But in this case, for the remote flash, we also need 208 servers. So it's 250 terabyte divided by 1.2 again. So in this example, we needed the same amount of local flash servers and remote flash servers, but at each remote flash server, we're paying a little bit of cost for the extra CPU and RAM. So in this example, it's 1.13 times more expensive. So this might be a little bit counterintuitive, because at the same queries per second, when we needed more disks, the remote flash became more expensive. Initially, I didn't really get it. So what has happened in this example is, in the previous examples, where it was 10 million queries per second and 100 terabytes, it was compute heavy. So we needed a lot more local servers. But in this example, the compute and the storage requirements are reasonably balanced, and we need the same amount of remote flash and local flash servers. But as we know, when we purchase a remote flash server or whatever, we need to add the cost of the CPU and RAM for the flash servers, and they call this a tax for disaggregation, which ultimately makes the remote flash configuration more expensive in the end. And they go through a few implications for the future in this paper. The first, it's not directly related to the disaggregated flash or stuff like that, but with their target applications, they only saw a 20% penalty for remote flash access. But when they just did a small micro benchmark, they saw 70% overhead. And the conclusion was that CPU resources are still being saturated by these real applications. So RocksDB in this case, even when accessing local flash. So in general, application software overheads are sort of still dominating the whole cost of a query. And the second one was that they say we still need to improve overheads in the network storage stack. So in this case, about 260 microseconds were added to their tail latencies, but it was okay for their target applications. But they asked, what about applications maybe now or in the future where the requirements are at the microsecond scale? It wouldn't have been acceptable in that case, especially with the new flash disks, which opens up questions about user level stacks and the RDMA. And from what I know, RDMA is quite popular now, I think. So just to conclude, at the time, flash was really gaining traction in the data center, but effectively balancing all these resources when application requirements change over time could be quite difficult. But because Flash has really low latency, can storage disaggregation be useful in this case, considering the overheads of the network? So this is maybe the main question they ask, and they just evaluate it with ISCSI, and they show that it can be pretty cost effective, even given the overheads of the network and the hit they took in queries per second and stuff like that. But it could still be very cost effective, especially in the future, given better protocols and stuff like that. Okay, thank you.